Lastly, we talked about trying to compare Chapter 15 approach to a problem, linear differential equation, non-homogeneity that had a discontinuity. And we did the first order one, and I did an example. Then I illustrated what would have to be done if it was second order, and time just didn't suggest that I could fit it in. So here's what I want to do in this particular video. I want to solve this second order differential equation. It is one of the exercises. In the exercises, you're probably going to use Laplace transforms. Purpose here is, yes, to use Laplace transforms and to compare with Chapter 15. So we're going to solve this differential equation, these initial conditions, where this is the non-homogeneity, right? If I draw that non-homogeneity, it is 0 up to pi, and then it is sine t thereafter. So sine t goes like this up to pi, and then it goes like this. Right? And on and on and on. In effect, then, it really doesn't have a discontinuity. It does because there is no dot here, but I could fill in that dot by putting an equal here or putting an equal here. So it really doesn't have a discontinuity, but it's got a piecewise defined non-homogeneity. And that's exactly the same as if there's discontinuity, right? Chapter 15 is what we want to attack with. It means I have to break the problem up to do it here and then there and kind of match. So away we go. For 0 less than t less than pi, we will be looking at y double primed, 4y primed, 3y equal to 0, along with y at 0 is equal to 1, and y primed at 0 is equal to 2. Linear, second order, homogeneous, constant coefficient differential equation. So pull out your auxiliary equation. M squared, 4m and 3, and I've made it nice so that it factors. Solutions then being -3 and -1. And therefore, y of t is equal to c1 e to the minus 3t, c2 e to the minus t, and don't need a y sub p because it is homogeneous. We'll use our initial conditions to find the c1 and the c2. 1 is equal to, when I put in 0, c1 plus c2. 2 I'm supposed to get when I differentiate and put in 0. So I get minus 3, c1, and then minus c2. And I solve these. I don't want to solve them, and you get that c1 is equal to 5 halves, and c2 is equal to minus 3 halves. Let's at least check that, okay? If I add them together, I'm supposed to get 1, that is true. I take minus 3 times this one, right? Minus 3 times that one, and then 3 times that one. Minus 3 times that one. Take minus 3 times that, it's minus 15 over 2. And then plus 3 over 2. That doesn't turn out to be 2. 5 halves. 2 is equal to minus. Oh, wait a minute here. I put them in the reverse order. Ooh. Okay. I put this one as C1 and I put that one as C2. So I assume then that this one's got to be C2. And that's a good thing I checked. Oh, now let's check those. If I add them together, I still get 1. Good. Then if I take minus 3 times this one, that gives me 9 halves minus 5 halves. That's 4 halves. Good. Glad I looked at that. All right. So the solution then is, let's call it y1. y1 of t is equal to, so for 0 less than t less than pi, the solution is, the c1 is minus 3 halves e to the minus 3t plus the 5 halves e to the minus t. So there's our solution. Now we'll go to t bigger than pi. What we're now looking at is y double primed, 4y primed, 3y is equal to the sine of t. Now, using this part of the non-homogeneity. To solve this, since we've got constant coefficients, non-homogeneous, we'll produce a y sub h, we'll produce a y sub b, we'll add them together. Y sub h, you agree, is going to be exactly the same as this guy was here. So y sub h of t, let's call them d1 e to the minus 3t and d2 e to the minus t. We need a y sub p. We need a particular solution to this. We'd ask, is it rule 1 or 2? Well, clearly it's not rule 2. That guy is not in here. So we'll write then a sine t and b cosine t. We'll substitute that into the differential equation and we'll solve for a and b. I'm going to tell you what the answers are, I hope. Right? So if you do that, right, so substituting into the differential equation, being like that, leads to y sub p of t is equal to 1 over 10 sine t minus 1 over 5 cosine t. But you have to do that, right? I'm just avoiding all that calculation, but visualize this is part of the process for chapter 15. So we can now say, I don't think I need that. So we can say that y sub 2, so for t greater than pi, let's call it y sub 2 of t is equal to d1 e to the minus 3t, d2 e to the minus t, plus y sub p 1 over 10 sine t, minus 1 over 5 cosine t. So here's the solution up to pi, here's the solution after pi. What we now want to do is we want to make the solution continuous and have a continuous first derivative. For solution on 0 less than t less than infinity, right, demand that it be continuous and have a continuous first derivative. At t is equal to pi. So we'll demand that. I think I need that, so let's leave that, and let's put that over here because I've got the y sub 2. All right. So in other words, we're demanding, maybe we could write it here, that the limit as t approaches pi from the left of y1 of t be equal to the limit as t approaches pi from the right of y2 of t. And then the same thing with derivatives. Limit t approaching pi from the left of y1 prime t equal to limit t approaching pi from the right y2 prime t. And let's write those here. So, okay, first condition, take your y1 function. y1 function, that's him here. Take the limit as t approaches pi, minus 3 halves, e to the minus 3 pi, plus 5 halves, e to the minus pi. So that's that. Now take the limit of the y2 guy, that's him, equal to d1 e to the minus 3 pi, d2 e to the minus pi, plus, limit is t equals to pi, gone. T approaches pi plus a fifth, plus 1/5. 1 over 5. So that's that one. Now this one. Differentiate this and let t go to pi. So minus 3. This one first. Okay? We're doing the y one first, this one. Differentiate 9 over 2 e to the minus 3 pi minus 5 over 2 e to the minus pi equal to. Now differentiate this one minus 3d1 e to the minus 3 pi. Brought down the 3. Next one minus d2 e to the minus pi. Now t going differentiate. Differentiate turns into cosine. Minus 1/10. Minus 1/10. Differentiate turns into sine. Gone at pi. So what do we now have? Two equations of d1 and d2. So solving for d1 and d2. I'm going to tell you what it is, but I'm not going to solve those. d1, d1. Let's make sure I got the right one in the right place. d1 is that which sits in front of e to the minus 3t. d1 is, okay, so it's d2. So d1, all right, so d1 is going to be this one. So d1 is equal to minus 3 halves, 1 over 20 e to the 3 pi. d2 is equal to the other one, 5 halves, minus 1/4 e to the pi. And so now we finally have the solution. Right? We can say the solution up to pi is this, and the solution up to pi is this, that d1 and that d2. So there's chapter 15 at work on this problem. And I left out a considerable amount of domestic calculations, especially from here to here. That's kind of, now notice they are linear equations, so you could say, take this one over here, and take that one over there, and then you could use Kramer's rule if you want. I don't care how you solve it. But it's not going to be particularly pretty. All right, let's go back and compare. So perhaps we should summarize it by saying that. Let's write down the final solution. Let's write. So final solution is y of t is equal to up to pi. Up to pi, it was this one. So 5 halves e to the minus t minus 3 halves e to the minus 3t. 0 less than t less than or equal to pi. And then after that, it's going to be d1 minus 3 halves plus 1 over 20 e to the 3 pi multiplying e to the minus 3t plus d2 5 halves minus 1/4 e to the pi multiplying e to the minus t plus 1 over 10 sine t minus 1 over 5 cosine t. And this is for t greater than pi. So there's our ultimate solution of this problem, again, using chapter 15. Let's go back now and say, suppose we use Laplace transforms instead. Taking Laplace transforms. All right, so for this one, the second derivative, s squared, big Y, minus s times that, minus that, minus 2, plus 4, Laplace transform of y prime, s, y minus 1, plus 3, big Y, equal to the Laplace transform of this guy. Let's write it as a Heaviside. Would that be Laplace transform? Turn the sine function on at pi. Does that take care of this? Right? That's an on switch. This is an on switch, and we're turning them on at pi. Equal to that Laplace transform of this. Maybe I should put our chart back up again for a moment. So the property we want to use is that, right? We've got the Laplace transform of something times a Heaviside. What does that property say? It says it is e to the minus as, e to the minus pi s. Take the Laplace transform of, and we're writing this one now. Take the f function, put in t plus pi. Sine of t plus pi. So there's that. We need to do this. So I guess we can turn this off momentarily. Equal to e to the minus pi s. The Laplace transform, if we did a trig identity, sine t cos pi plus cos t sine pi. Sine t cos pi, that's minus sine t. Cosine pi, sine cos, cos sine, that's gone. So there. So enter then minus transform of sine s. No, 1 over s squared plus 1. E to the minus pi s. So there's the transform of then our non-homogeneity. Solve for big Y. Big Y of s is equal to everything with no big Y to the other side. That's over s. That's over 2. There's a 4, that makes 6, plus 6. That's everything over, plus what's over there now, minus e to the minus pi over s squared plus 1. All over s squared, 4s, and 3. How does that look? Let me check that I haven't drawn it already. All right, that looks good. S squared plus 1, all right. Looking good. So last step in, invert this. Always again, the biggest problem with Laplace transforms is the inversion process. I would suggest that we write this as this one over this one, and this one over this one. So writing then s plus 6 over factorand s plus 3, s plus 1, minus e to the minus pi s over s plus 3, s plus 1, s squared plus 1. So we'll partial fraction that, we'll partial fraction this, and we should be ready. And I hope I've got that written down. But it appears that I do. All right. So let's have that over here. So I can then put the overhead back up again. Now this one is an easy partial fractions. That's handy dandy covered. Great. So equals then, I have here 5 halves over s plus 1 minus 3 halves over s plus 3. And then I have minus e to the minus pi s, e to the minus pi s, and the partial fraction decomposition up. Minus s over 5 plus 1 over 10 over s squared plus 1 plus 1 over 4 over s plus 1 minus 1 over 20 over s plus 3. That's what I have written down. So now we're prepared to invert. So y of t is equal to. So hopefully I can take this off, put our table back up so we can constantly refer to it. So putting it back up. Inverting then. This one. 5 halves e to the minus t. That's just that very top line. Minus 3 halves e to the minus 3t. That takes care of that. Now this one. This one, what are we doing? We're looking at this property here. We've got e to the minus as, or a is pi. And this is the other one. What does it say do? It says, go find him. Him is the inverse of him. Every time you see a t in it, drop in t minus a, drop in t minus pi. So we're going to invert this, and every time we see a t in it, we'll drop in t minus pi. So we look at that one over that one. That's a minus 1 over 5. That's out. Then we've got that. That's a cosine. The cosine of t, but we're dropping in t minus pi. So that's that. Now we got this one. That's a sine. 1 over 10, the sine of t, but we drop in t minus pi. And we've got this one, plus 1/4 e to the minus t, but we drop in t minus pi. Minus 1 over 20, e to the minus 3t, but we drop in t minus pi. And then we multiply that by h of t minus pi. So there's our solution. We could simplify this, and we could simplify this. Cos, cos, minus sine, 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 cos, cos, sine. So those can be simplified. I think you can do that if you wish. If you look back at the solution we got by chapter 15, and you look at the y1 piece before pi, if you look at before pi, this would be gone. That, as I recall, was the solution we saw. And when you have bigger than pi, you put a 1 here, and you then combine that one. No, I guess you can't combine them, not quite the same. And here, right? But you'd have that y2 guy. So there's the solution of Laplace transform. Again, which do you prefer? Me, I would prefer the Laplace transform as to the solving separately and matching. But it's a choice that you make when you got a problem that you want to do. On an exam, I may tell you what to do. If I don't, you could do it either way that you wish. What I would like to do is one physical example today, and then some more next day. So the one I would like to do is example 6.29. So example it refers, it says, find the amount of salt in the tank of example 3.10. If pure water is added for the first 10 minutes, and then salt mixture is added thereafter. Now you don't have access to example 3.10, but I'll tell you the details up here. So we have the following. We have a tank. In this tank is 1,000 liters of water, in which has been dissolved 5 kilograms of salt. You have stuff coming in, right? Now, in the previous example, it was coming in, right, it is a concentration of 2 kilograms per 100 liters, and it's coming in at 5 milliliters per second. That was in the old example. In this example that we're doing in this chapter, it's saying that's going to be coming in later. For the first while, for the first 10 minutes, was coming in as pure water. All right? At the same time, well-stirred mixture is coming out at 5 milliliters per second. Right? And the question is then, how much salt in the tank as a function of time t? Right? But first, again, this is what's coming in after 10 minutes. What's coming in before 10 minutes is pure water. Right? Just dumping pure water into there. Right? So let's say let. Now normally back in, we did this kind of problem back in section 15.3, these tank problems. Right? Normally what I would say is let S of t be the amount of salt. But that is a bit of a problem because we like small letters here and big ones for transforms. So I can't use that. And I don't want to use an S. Okay, that's going to be very confusing. So let's let X of t. Did I use that in the book? Did I use X of t? I did. All right, so let's do that. Let X of t be number of grams of salt in tank as a function of time t in seconds. Now remember what we did back in section 15.3, we said symbolically, dx dt is the rate of change in the amount of salt in the tank, and that means the rate that is coming in, rate salt in minus rate salt out. And so we had to figure these two things out. So let's concentrate on those for a moment. Rate in. So let's concentrate on the rate that's salt in. For, could we say for 0 less than t less than 600, for the first 10 minutes, the rate in is equal to 0. There's no salt, pure water is coming in for the first 10 minutes. Then we started to add that stuff there. Okay, all right. For t larger than 600, we want to know how fast it's coming in. Remember the idea back in 15.3 was to say, what we need is the concentration, and then multiply that by the volume rate out. But because this is with units, this is mils per second, so we need this one in grams, because we're working in grams, per mil. So we want to turn this into grams. We multiply by 1,000. To change this into mils, we multiply by 1,000, and then we would do this. Right? That will be the rate in. Right? So what do we got then? That's 1 over 10? 1 over 10. Rate in for that. Rate in is equal to 1 over 10 grams per second. All right. Now let's talk rate out. Rate out. Same idea. What we need is the concentration of salt in here multiplied by volume rate out, which is 5. 5. 5. 5. We need the concentration of salt in here. Concentration of salt in here is how much salt divided by the volume. How much salt is in here? Answer, I don't know. That's what I'm trying to find out. So we'll put an X. And the volume. Well, do note that it's coming in at 5 mils per second. It's leaving at 5 mils per second. Therefore, the volume inside is never going to change. It's that, which we would now multiply by 1,000, turn it into liters. All right, so there's the rate out, right? There's the rate in. So we can feed it in and say, equals rate salt in. Well, it's this and it's this. Could we write this as f of t let's describe that function in terms of Heavisides. Could we simply say that it's 1 over 10 times h of t minus 600? Right? We're turning this guy on at 600. All right? So that's that guy. So we'll simply put f of t here for a moment. Minus rate solves out, that one's that one. So 5x over 10 to the 6. So how does that look to you? Or, right, dx dt plus 5x 10 to the 6 is equal to the f of t. How does that work? All right? All right. So Laplace transforms. Hope we don't have to look at this. Hope I got it right. So taking Laplace transforms. And we have here Sx at 0 is equal to 5,000. There was originally 5 kilograms. So taking the Laplace transform for the derivative, Sx minus 5,000 plus 5x over 10 to the 6 equal Laplace transform of the f of t, which I just erased. It was equal to 1 over 10 h of t minus 600, correct? I hope so. Let me check it. I think that's what we wrote down. 1/10, yes, equals them. Laplace transform 1 over 10 e to the minus 600, yes. Solve it. X of x is equal to 5,000, over you go. You stay there. And then divide by s plus 5 over 10 to the 6th. So there's the Laplace transform. What we want, all we have to do is invert it. So invert it. So inversion x of t is equal to this one, inverted, 5,000 e minus 5t 10 to the 6. So that should be an inversion of that one, plus 1 over 10. Inversion of this one, same thing, but we drop in t minus 600. So e minus 5 t minus 600 slash 10 to the 6. Tag on Heaviside, h of t minus 600. All right? So let me check and see whether that's what I wrote down. Yes, sure. 357. Somehow it doesn't look like it. What did I forget? Oh! It's gone. When you take the Laplace transform of the Heaviside out of this, it's supposed to be over S. So that's going to change things somewhat. So that S is going to be sitting in here. And then we're going to break this up into 5,000 over s plus 5 over 10 to the 6 plus 1 over 10s, s plus 5 over 10 to the 6, e to the minus 600s. So this one we did over there, but that one we're going to have to partial fraction. So 5,000 over s plus 5 over 10 to the 6 plus, presume I've got the partial fractions written down somewhere. Is it that one? 357, 358. All right, so partial fractions is 1 over 10, 10 to the 6th over 5 all over s, 10 to the 6th over 5 all over s plus 5 over 10 to the 6th, e to the minus 600s. So if we invert, and let's take this one off temporarily, we still got that one coming from this one, right? Then we're going to have 1 over 10, and we're going to invert this one. That's 10 to the 6th over 5, 10 to the 6th over 5. That's the inversion of that. Then this one we've got minus 10 to the 6th over 5. And that's going to be an exponential, e to the minus 5t over 10 to the 6th. But instead of the t, we're going to drop in t minus 600. And then we're going to multiply all of that by h of t minus 600. So that should get up, but I think I simplified these numbers down to top one, staying the same, 5t over 600. And then I took these, I pulled out the 10 to the 6 over 5, pulled that out, canceled it down, and got 20,000. And then 1 minus e to the minus 5, t minus 600, slash 10 to the 6, h of t minus 600. So there's the ultimate solution of it, right? So compare, or again, think about that relative to what you would have done without Laplace transforms. Chapter 15 would have said, solve it from 0 less than t and less than 600. Solve it for t greater than 600. Then match the solutions at 600 to reduce, right? This, to me, is easier. Right? We have partial fractions here, but both of those partial fractions, that partial fraction can certainly be done mentally. It's non-repeated linear factors. So there then is an example of Laplace transforms, again at work with a piecewise defined non-homogeneity. So next day what I'd like to do is talk about same kind of scenario, second order one, in the context of vibrating mass spring system.